Hi, this is Professor Stugard, and in this video, we're just going to go through a bunch of different examples of limits. So our goals for this video are to work through several different limit examples, and the real idea is we want to make sure we understand these different techniques that we can use to evaluate different types of limits. And of course, when we can apply these, what we look for, what we can use, and hopefully that will help us in the future when we come up against different limits for different types of problems. So we're going to start off with this example. The limit as x approaches 2 of x squared minus 4 over the quantity x squared plus 4. Make sure you're following along. Make sure you're writing this down, right? You're writing each problem down. You're doing this yourself. You're not just watching me, right? I know I'm really, really good at this, but you're not going to get any better at this if you're not the one practicing and writing this down too. So the first thing I should always try with these limits is direct substitution, right? If I have a polynomial or a rational function or an exponential or a trig function, direct substitute first. If I get a valid number when I direct substitute, right, when I plug it in, then I'm done. That's just going to be my answer. So try the easy thing first. So I'm going to plug in 2 everywhere I see an x. That is the direct substitution. And so on the top I get 2 squared minus 4. On the bottom is 2 squared plus 4. 2 squared is obviously 4. So 4 minus 4 over 4 plus 4. So I'm going to get 0 over 8. And is 0 over 8 a valid number? Well, yes, right? 0 divided by 8 is just 0. 0 is a number as valid as any other number on our entire number line. So absolutely, that is a valid limit, which means that is my answer. And that's it. I'm done with this problem. I can move on to my next problem. Example 2. Now I have the limit as x approaches 2 of x squared minus 2x over x squared minus x minus 2. And same idea. I have a rational function here, so I'm just going to direct substitute. I'm going to plug in 2's everywhere that there's x's and see what happens. So on the top, 2 squared minus 2 times 2, which 2 squared is 4, minus 2 times 2 is 4, so 4 minus 4, so I have 0 on the top again. And my denominator, 2 squared is 4, minus 2 is 2, minus 2 is 0, so I end up getting 0 over 0. So does this limit exist? No, this is an undefined quantity, right? I cannot divide by 0. That means that this is an indeterminate limit. Now, the limit does not exist right now. Indeterminate, though, is a special term that we give to a special set of limits. So indeterminate form is anytime we take a limit, we try direct substitution, and we arrive at one of these forms. So the first would be 0 over 0. And again, we know we can't divide by 0. It's indeterminate. Similarly, infinity over infinity. Well, which infinity is bigger? The top one or the bottom one? Or is it the same size? Or, oh yeah, that's right. Infinity really isn't a number. It's a concept of growth. So it says the top is growing without bound. It says the bottom is growing without bound. Well, depending on how they are growing without bound, we could get different answers for what's going on, right? Maybe the top is growing faster than the bottom, or the bottom is growing faster than the top, and all right, this is going to be something that we're going to have to dig a little bit deeper into a little bit later in the course. Similarly, 0 times infinity is also indeterminate because is the infinity big enough to cancel out the 0? Or, I don't know. It's indeterminate. Similarly, infinity minus infinity. Well, how does that work? Well, does that make sense either? And again, not really. My favorite one here is 0 to the 0. This is indeterminate. And it might be a little confusing why, but don't forget that 0 raised to any power is always 0, right? 0 squared is 0. So 0 to the anything is 0, except we also know that we have this other rule that anything to the 0 power is equal to 1, right? 2 to the 0 is 1. So is it 0 because it's 0 to a power, or is it 1 because it's something to the 0 power? Or is it in between? Is it a half? Oh, I don't know. Again, it's indeterminate. We'd have to do more work to try to figure out what that limit actually is. Similarly, infinity to the 0 is also indeterminate. What happens when you raise infinity to a 0 power? I don't know. We got to do more work. Again, these indeterminate limits, these indeterminate forms, this means that the limit might exist, and we'll just have to use our knowledge of functions to try to simplify and rewrite the problem before we do the direct substitution. It's also completely possible that the limit does not exist. Indeterminate form simply means that we need to do a little bit more work before we actually get to what the right answer should be. So let's go back to this problem. Again, we have my indeterminate limit, and we got to do something else. Well, remember, the whole concept of limits is we're basically saying what should happen, not what happens at x equals 2. We know that at x equals 2, the bottom is 0, so it's undefined. But what happens really, really close to 2? If I get really, really close to 2, what probably should have happened instead of this function being undefined? And so, again, the genius of this limit notation is we're saying, okay, we're really close to 2. It's not 2. So I can do all my algebra, right? I can use my knowledge of algebra and trigonometry and everything else. I can bring it together and I can try to simplify this. And then after I simplify it, then I can direct substitute later at the end and see if that actually solves my indeterminate problem. Now, again, like I said, make sure you're taking the time to write everything down here. And so the first thing I'm going to do here with a rational function, I'm going to try to factor the top and the bottom individually. So make sure you take the time, write this out, pause the video as you need, and pause it right now because I want you to factor the top and the bottom individually on your own. Check your answers by multiplying it back together. All right, did you do it? Did you factor? Did you pause? Are we done? Can we move on? All right. So the factorization, my numerator is x times the quantity x minus 2. That's because on my numerator, the only thing I can do is factor out that common x, right? My GCF, my greatest common factor is the x. I can pull that out. That's the only thing I can do, and then that'll leave me with x minus 2. The bottom is a trinomial that I can factor with the AC method or guess and check, and I get the quantity x plus 1 times the quantity x minus 2. So again, I'm getting to do all this algebra. Notice that limit notation is still present. I have not gotten rid of my limit notation. That needs to be part of every single step throughout the problem. All right, the notation is really, really important. Until we actually go ahead and do that direct substitution and get a valid answer, we need to keep that limit notation. Every single line should have that LIM as we move down our page. Okay, but I can do some algebra here. I can cancel those x minus 2's, right? I have a common factor, so I can cancel it. Now, again, I hate the word cancel in this case because it doesn't really cancel. It doesn't disappear. What we're saying is x minus 2 over x minus 2 is equal to 1, right? Anything over itself is always equal to 1. So I'm really multiplying by 1, which doesn't change anything. So be careful with the term cancel. But anyway, I cancel the quantity x minus 2. That leaves me with x over x plus 1. So now I'm going to try direct substitution at this point, right? So I'm going to see if I get a valid answer. Well, and the direct substitution at this point is pretty simple because x is 2, 2 plus 1 is 3, so I just get 2 over 3. That is absolutely a valid number, and that is a valid answer, and that is the solution to this problem. This limit is equal to 2/3. All right. So, again, we can always factor and cancel as long as we keep that limit notation and then direct substitute at the end. Next example, the limit as theta approaches 0 of tangent theta over sine theta. Okay, so I have trig functions. Let's try direct substituting. So we're going to plug in 0 everywhere that there's a theta. So I get tangent of 0 over sine of 0. Now, if you were taking a calculus class, you should know your trigonometry. You should know your unit circle. You should know your trig identities. And we should know what the values of sine, cosine, and tangent are at all of the major points around my unit circle. If you don't, make sure you learn that. Fill in that gap. Most people don't have trouble in calculus class because they don't understand the calculus. Most people have trouble in the calculus class because they have gaps and they refuse to do the work to fill in those gaps. And the foundation that we're trying to build calculus on crumbles because it's just not there. So make sure you take the effort to learn these things. Right? You don't want to have to go to a book or a calculator every single time you need to evaluate simple things. That's going to destroy your flow. Right? Imagine if every time you were writing an essay, you had to look up in a dictionary how to spell every single word. Your writing would be terrible. You need that flow. And understanding these basics of mathematics will help with your flow and will help everything else go so much smoother. So, we should know that tangent of 0 is 0, and sine of 0 is also 0, so I get that 0 over 0 when I direct substitute, which is, of course, an indeterminate limit. Now, what can I do with my indeterminate limits? Well, first thing I'm going to look at is some of my trig identities. And we'll go with the most simple and obvious trig identity given this problem, and that is for tangent. And we know tangent is really sine over cosine. So tangent theta is sine cosine over cosine theta. Yeah, so tangent theta is sine theta over cosine theta. And so I can always try to reduce this problem to just sines and cosines and see what happens. So I'm going to make that substitution. I'm going to replace my tangent in my numerator with sine over cosine. Now I end up with a complex fraction, right? I have a fraction inside of a fraction. That's a complex fraction. But we know how to deal with these. If I want to divide fractions, I need to multiply by the reciprocal. So I keep the numerator the same. That's my sine over cosine. And now I need to multiply by the reciprocal of sine, which means I'm going to be multiplying by 1 over sine. So, all right, so now I have sine theta over cosine theta times 1 over sine theta. What am I going to do? Well, oh, wait a second. I have a sine theta on the top and the bottom, right? My numerator and my denominator both have a sine theta. I can cancel that out. Really, it just equals 1, but I can cancel that out. And so that leaves me with the limit as theta approaches 0 of 1 over cosine theta. And, well, if I direct substitute now, cosine of 0 is 1. I get 1 divided by 1, which is 1. 1 is obviously a valid answer, and so that is the solution to this particular limit problem. On to example 4. Let's say I have the limit as h approaches 0 of the quantity x plus h squared minus x squared, all divided by h. So again, I basically have polynomials and rational functions here, so I'll try direct substitution. I'm plugging in the 0 for the h though, right? Even though I have multiple variables, the only thing that actually counts as my variable here is going to be the h, right? I know x is typically our variable, but in this case, again, we have to pay special attention to our notation. X is being treated kind of like a constant in this case, and h is the function that, h is the variable that we are changing in this function. I want to know what happens as h gets really close to 0 from both sides. So if I plug in 0 for my h's with direct substitution, immediately my denominator is 0, which is a problem, which means I need to do a little bit more work. I can take a look at the top. X plus 0 is just going to be x, following my order of operations, right? Adding 0 does nothing. X squared is x squared, so x squared minus x squared is 0. I do get 0 over 0. I get an indeterminate form, which probably means there's more I can do here. So where should I start with this problem, since I have an undefined or indeterminate limit with direct substitution? Well, I think the best place to start here is probably to go ahead and to expand that binomial, right? X plus h is a binomial. There's 2 terms. And I want to expand that. That means multiply it all the way out. It basically means FOIL. So again, pause the video. I want you to expand and write out x plus h quantity squared. Did you get your answer? Because then you can unpause. And so when we expand that binomial, I should get x squared plus 2xh plus h squared. If you thought it was just x squared plus h squared, shame on you. Go back to high school and apologize to your math teacher. We can't be doing that. You got to write it out, x plus h times x plus h, and multiply the whole thing. FOIL it out, expand that binomial. Okay, so I make that replacement, and now I'm taking a look. So I have x squared plus 2xh plus h squared minus x squared. Again, all these variables, but I do have something that cancels. I can cancel the x squared minus x squared, and that'll be 0. And that will truly cancel. I'm not even putting air quotes around that, because that is 0. So that leaves me with 2xh plus h squared over h. Well, now when I look at my 2 terms that are left in my numerator, they each have an h. So let's try factoring. So if I factor that h out of my numerator, I'm going to get 2x plus h divided by h. Oh, and now I can cancel h again, and I'm just left with the limit as h approaches 0 of 2x plus h. And yeah, I can direct substitute here. If I plug in the 0 where the h is, well, that's 2x plus 0, which is just 2x. And that is an absolutely valid answer here. That's it. Yeah, not too bad. So make sure you can expand binomials. The binomial theorem is another place where people sometimes have a gap. Knowing the binomial theorem will make life a lot easier, especially if we can, do Pascal's triangle, right? Pascal's triangle related to the binomial theorem and all that cool stuff, and combinatorics as well. it will definitely make your life a lot easier. Although, again, you can always write it out in FOIL as long as you're careful. All right, example number 5. Let's say I'm given this function f of x, which is a piecewise function. So the x squared plus 1, where x is less than 1, and the quantity x minus 2, where x minus 2 squared, when x is greater than or equal to 1. And so I want to know, what is the limit as x approaches 1 of this function? Well, this function, like I said, is a piecewise function where that subdomain actually switches exactly at the point that I'm trying to investigate, which is x equals to 1. So I want to know what's happening. The limit as x approaches 1 means what happens from the right-hand side, what happens from the left-hand side. Are they approaching the same limit? So I'm going to have to use those one-sided limits here, especially because, because specifically this is a piecewise function where that is switching what my actual rule or my function is. Okay, so we'll take a look at that left-hand limit. Remember, when we're doing the one-sided limits, our notation is we add a little negative sign or plus sign after the value in our limit notation. So the left-hand limit, we're coming from the left-hand side, values smaller than 1. So x approaches 1, the little minus sign of f of x. Well, at values less than 1, the function's going to behave like x squared plus 1. So I really need the limit as x approaches 1 of x squared plus 1. I just have a polynomial. It's direct substitution. X squared is 1. 1 plus 1 is 2. So my left-hand limit is 2. Now I need to look at my right-hand limit. So again, the notation here, x approaches 1, and I put that little plus sign there for f of x. Now, these are the values bigger than 1. So when x is greater than 1, well, then it's the quantity x minus 2 squared. So again, I have a polynomial type function. I don't have to expand because I can just plug it in. And if I plug in 1, 1 minus 2 is negative 1. Negative 1 quantity squared is positive 1. So I have my left hand and my right hand limit. I ask myself, do both of my one-sided limits agree with one another? No, they do not. 2 is not the same as 1, which means the limit as x approaches 1 of my function does not exist. All right, so we did a couple examples together. Now it's time for you guys to try. So here are 4 limits for you guys to try to evaluate on your own. Again, try direct substitution first. If that doesn't work and you end up with an indeterminate form, either use your knowledge of factoring, use your knowledge of how fractions work, use your knowledge of trig identities, and then lastly, just do a piecewise limit. All right. So if you have any questions on any of these, let me know. Good luck evaluating these limits, and as always, take care of yourselves.